So today we'll continue on from last time when we introduced the idea of the second order differential equation. Now what I want to do today is to find a particular solution to an ordinary differential equation. Last time, the video for last time goes through how you come up with a general solution, and we'll talk about that as we go along, because part of today will be finding the general solution and then going on from there to find a particular solution. So we will be reviewing the process that we go through in the previous video. To be able to find a particular solution, as was suggested last time, you need some boundary conditions. So here are some boundary conditions. So we have a differential equation, and this could relate to, if you think back to that previous video, it could relate to some oscillation where we've got a mass on a spring. So this first part might correspond to the force on the spring due to gravity, where there's an acceleration. d2x by dt squared talks about the acceleration of the body. Excuse me. There's also an element that talks about the drag factor of this oscillation. So this part of the differential equation is about how the drag, what the drag is on the thing in the liquid that it's in, or in the air even. So it's to do with some constant, the viscosity of the liquid, and also the velocity, and dx by dt. Why have I written dt by dx? dx by dt. dx by dt. The rate of change of displacement with time gives us the velocity. So perhaps you just change that. dx by dt. A bit of light relief in the video. And then this final bit, which is the spring constant. So the force on the object is due to the displacement and some constant, as we talked about last time. So we can end up with a general solution to that equation, and we will quickly review that, but then we can put some initial conditions in and find out the actual relationship to describe the motion of this object. So let's have a go. So we've got 4 d2x by dt squared plus 3x, 3 dx by dt minus 6x equals 0. That's our differential equation. d2x by dt squared, yes, this is a convention to mean the second differential of x with respect to time, and that gives us the acceleration. So the first differential gives us the velocity, dx by dt, and if I differentiate the velocity, it gives the acceleration, doesn't it? And if you think about the differential of the velocity, that's the second differential of the x. So that's where that comes from. Okay. Incidentally, it's also worth pointing out that because this right-hand side is 0, this means this is a free oscillation. You displace it and then you let it go and it oscillates, and that oscillation will die away to 0. That's what we mean by a free oscillation or free vibration. If the right-hand side is not 0, that means there's some sort of driving force going on, which is keeping the oscillation going. So some sort of driving function. And that's what we're aiming for in the end, solving equations that have a function on the right-hand side. So as was outlined last week, the first step here is to form what's called the auxiliary equation. Which means we just replace the d2x by dt squared by an m squared. Replace dx by dt by m, and the number x has gone. And that gives us a quadratic equation to solve that we use using the quadratic formula. So m equals minus b plus or minus the square root of b squared minus 4ac all over 2a, which will give us values for m. M equals, and then we can just quickly work that out. So m equals 0.9 or minus 1.66. So two possible values for the solution. So that gives us our auxiliary equation. So these are two real distinct roots. And if we refer back to that table of results that you can see on the notes from last time, there's three possible solutions for the general differential equation. One is where we've got two real different roots. That's this first case, that's the one we've got here. The other possibility is we just get one solution where it's real but both roots are the same. And the third possibility is if we get complex roots where we get the negative root. So then we'll be having, I actually went through an example of each of those last week that you can have a look at. But today, well, what's happened here for this particular example, we end up with this. So the solution is of this form: y equals a e to the k1x plus b e to the k2x. So the solution, the general solution, is y equals a e to the k1x plus b e to the k2x, where k1 and k2 are our two answers, 0.9 and minus 1.66. So therefore, for this particular example, i.e. y equals a e to the, and it doesn't matter which one we call 0.9, so 0.9x plus b e to the minus 1.66x. And that's the general solution, or the complementary function. And that's what we did. That's what last week was about, in a way, looking for that general solution. Now, we want to go a step further and find a particular solution using the initial conditions to find the values of a and b. Okay, so now, insert that page. Now, use the boundary or initial conditions to find the values of a and b. And hence arrive at the particular solution. So what are these initial conditions? Let's go back to the original question. At t equals 0, x equals 3, and dx by dt equals 0. Where'd it go? Oh yeah. Oh yeah, there we go. So, how do we do it? Well, we've got our solution. Oh, for heaven's sake. How do I get rid of this? So back to this general solution again, which is here. Okay, what we need to now put in our initial conditions. So y equals 0.9x plus, try and see if I can do that again, edit, copy, go to here. So we know that when t, in this case of course, t is our variable, so really I should have written a t in there instead of the x. So in this case, x is the time variable, which is common, it's often the time. What we're seeing is what's happening to the x, the displacement, as time varies, so that would have helped if it had done that. So at t equals 0, x equals 3. So put in those conditions. When t equals 0, x equals 3. So putting those conditions into this equation, 3 equals a e to the 0, because 0.9 times 0 is 0, plus b e to the 0. And anything to the 0 is 1. So this is a very common thing to do. At t equals 0, that means that the power often becomes just 0, and anything to the 0 is 1. So we can write that 3 equals a plus b. And we've used our first set of initial conditions to find the first of two simultaneous equations, effectively. If I have two constants, which I have in this case, a and b, I need two sets of initial or boundary conditions to be able to find them. And in this case, I've got two sets of conditions. One, when t equals 0, x equals 3, and 2, when t equals 0, dx by dt equals 4. So I can use those two. Okay. And I've used the first one to find a simultaneous, one of a set of simultaneous equations. So then I put the initial condition, the second initial condition in, when t equals 0, dx by dt equals 4. So the first thing I have to do is take my formula, my equation, x equals a e to 0.9t plus b e to the minus 1.6t, and differentiate it. So dx dt will be, and when we differentiate an exponential function, the power comes down and multiplies by the number in front, and then the power of the exponential stays the same. So this will become 0.9a e to the 0.9t minus 1.66b e to the minus 1.66t. Now put the initial conditions in. So dx by dt equals 4. And again, t equals 0 when dx by dt equals 4. So we can write 0.9a, because e to the 0.9t is just 1, minus 1.66b. And we've got another equation. So that's the second of our set of two simultaneous equations. So putting them together, 3 equals a plus b, which was equation 1, we've got two simultaneous equations. So we've got our two simultaneous equations. All we've got to do now is solve them. What do we do? Any ideas? How would we combine them? Yeah, that's the sort of idea. There's two basic methods. One is elimination, where we make a or b the same in these two equations by multiplying or dividing by something. Or we use substitution, where we might rewrite equation 1, say, to read a equals 3 minus b, and then substitute that into equation 2. And let's try that way, okay? Because the elimination method is one that most people use, but often, especially in this case where we've got decimal numbers involved, it's easier maybe just to quickly use the substitution method, especially as this first one, number 1 here, is so straightforward. So let's use that idea. From 1, a equals 3 minus b. And then we substitute this into 2. And we can write 4 equals 0.9a, and a is 3 minus b, minus 1.66b. What do we do with this now? Multiply out the brackets. I heard somebody mutter 0.9 times 3. Well, what's 0.9 times 3? 2.7 minus 0.9b minus 1.66b. We can combine the b's. Minus 1.6 minus 0.9 is minus 2.56. Adding 2.56 to both sides, we get 2.56b plus 4 equals 2.7. Subtracting 4 from both sides, we get 2.56b equals, what's that, minus 1.3. And then divide both sides by 2.56 and we get b. Minus 1.3 divided by 2.56. And then we reach for calculator to get that b equals minus 0.51. Rounded to two significant figures. So we've got b. So once we've got b, we now put this back into a, substitute into a, into 1 rather, to find a. We had that a plus b equals 3. So b is minus 1.5. So minus 0.51 equals 3. So a equals 3.51. So putting these values into the complementary function the general solution that we had to this particular problem, we get the particular solution. x equals a, and a is 3.51, e to the 0.9t, and b turns out to be minus 0.51, so it's minus 0.51 e to the minus 1.66t, and that's the particular solution for this problem. So just to look at our solution, so what we have here is a situation where this differential equation that we started off with, got it the wrong way around. This differential equation here, I brought the wrong way down, has the solution x equals 3.51 e to the 0.9t minus, and we found out what that solution is. And if we plot this, we get this. So it looks like if we're plotting displacement on the y-axis and time on the x-axis, that the displacement from 0 is actually increasing with time. So we have a situation where the restoring force, which would be to do with this part of the formula here, this restoring force is not enough to overcome the force moving the oscillation, moving the object away from 0. So this could maybe be modeling some sort of satellite moving away from orbit, and actually the force of gravity is not enough to pull it back, so it's actually moving away and it's going to escape. It's not coming back down to 0 again. So let's have a look now at another example. Determine the general solution of that differential equation, 2 d2y by dx squared plus 5 dy dx minus 3y equals 0. Find also the particular solution given that when x equals 0, y equals 4, and dy by dx equals 9. So it's exactly the same sort of problem we've just been having to go at. You will need to refer back to, in last week's notes, this table with the roots on. So the solution you're going to get will depend on the solution to your auxiliary equation. If you get two real different roots, you look at the top solution. If they get one root and they're the same, it's this solution. And if you get a complex solution, you're looking at something like this. Notice in this bottom one we've got some cosine and sine waves, so that would imply some sort of oscillation about 0. So I'll just give you a little bit of time now to have a go at this question here.